Hello everyone. Today I would love to share our research about identifying linked incidents in large-scale online service systems. Large-scale online service systems like Azure will serve millions of services in real time, such as web applications, mobile applications, and the high demand of service availability calls for quick response for service incidents. However, in large-scale online systems, incidents occur frequently due to a variety of causes, from updates of software or hardware or changes in operation environment. As a result, dealing with these incidents caused by software or hardware is quite important. So let's first look at the cloud system structure. In general, for a cloud system, it always composed of many services and many components. For example, the figure above illustrates that there are 5 services in total for a cloud system. Services were divided by different functions. For example, Service A may be in charge of data source management, Service B may relate to the routing services, and etc. So each service will also contain their own components, and each component may be a specific virtual machine that store or responsible for a certain part of the function. For example, if service A is related to data management, then one of its components, like component A, it may relate to the data storage for certain area, like East US or East Asia. So, as mentioned before, the cloud system is likely to meet some problems. As in the figure above, if one component in service B occurs some instance, then other component in service B may likely to be affected and meet problems as well. So, meanwhile, some related services will occur outages as well. For example, when the disk is full, if we do not fix it, then the data loader server may get slower. And if the data loader gets slower, there may cause more requests from the front-end web applications. And data loader server may meet incidents as well because there are too many requests. And then other services will turn down together and the whole system will just black out. So the spreading of incidents make the incident linkage and mitigation services even more urgent. For a typical routine in the cloud system, when an incident occurs in large company, the on-call engineers will check the system logs and conduct troubleshooting actions. As the guardians of production, on-call engineers take care of their assigned operations by managing outages that affect the whole system and perform related operations to mitigate or completely solve the issue manually. Meanwhile, engineers will sometimes link several interrelated incidents for efficiency and effective diagnosis. For example, a few incidents are usually reported together due to the system dependencies, where mitigating one incident can well resolve another. Moreover, the links may represent other relevant information such as reoccurrence relation or co-occurrence relation between two incidents. So detecting and recording such related incidents are valuable for incident diagnosis. Large-scale online systems are composed of many services, and these services coupling with each other heavily. The incident may happen in one service and are actually caused by problems in another service. As a result, incident linkages discovered by on-call engineers can provide strong evidence on such coupling structure and bring insights to the full diagnosis. So let's first have a look at the typical ICM system in Microsoft. The creation of an incident in ICM system would immediately trigger the triage process, where on-call engineers in the ICM system would investigate and find the correct responsible component to take over the incidents. Once the responsible component of the incident is found, the on-call engineers will assign the component would try different actions to mitigate the incident. So after the incident is successfully mitigated, the engineers in the team will conduct a post-mortem analysis on the root cause of the incident, and they will also determine whether one incident should be linked to another existing incident, and label all the linked incidents accordingly, which is also known as the incident linkage step. So through the whole process, the incident mitigation step usually consumes a lot of time and labor resources. This consumption can be greatly reduced by transferring past time knowledge and solution to the current incidents by identifying the links. Therefore, this work focuses on identifying incident links for on-call engineers, as shown in the dashed line, so as to quickly find the mitigation solution as well as figure out the right root cause of the incident. Here we would love to introduce the different types of linked incidents. In general, there are three types of incidents. There are duplicate, there are sequential, and there is a special one, which is the cross-component incident links. So the first type is duplicate. Duplicate linkages are those linked incidents that refer to the same malfunction and described from the same or different perspectives. So the first line in the table, it shows the linked incidents, where the parent and child incident title are extremely similar, but with different styles of description. This is because in the ICM system, incidents can both reported by a human and online monitors. So the linguistic style of this description for the same instance can be both different and the same. So the second type is the sequential incidents. In large online service system, different components work jointly to support several online services. It's common that one incident may also affect the functionality of another, which leads to incidents that happen sequentially. For example, if storage of cloud system broke down, many products running on cloud system would probably be impacted. If we treat these incidents independently, it will largely ignore the rich information of the system interdependencies. As a result, in practice, linking these incidents together can also significantly help engineers understand the specific instance and better fix the incidents. And the third one, in the current system, is an important proportion of the instance. They are cross-component links, where two linked incidents belong to different components, which may be either duplicate or sequential. These links are strong indicators of underlying component structure dependency, which keeps evolving due to the frequent updates in the system. So, to deal with different types of linked incidents, we propose LiDAR, a deep learning-based model for identifying linked incidents. The overall structure of the proposed method is illustrated as above. To consider both the textual information and the system structure information, we extract two features from each incident for learning. The description of the incident in natural language and the corresponding component that is responsible for the incident. The two different features are fed into two modules, the text embedding module and the component representation module. First, to deal with the changes through the textual description from different sources, we introduce the text encoder that can capture the semantic representation of the incident description. And then, to understand the system architecture and dependencies, the component representation module is realized with a novel network representation learning approach. Each component in the system is learned to be embedded into a low-dimensional latent space according to their correlation, and other components according to the historical links. Finally, after calculating similarities from these two distinct modules, we integrated them together to obtain the final score and set a threshold for link identification. So firstly, the cloud system dependency is learned by treating all components as a network. Historical linkages are used to inspect component relations, and all these components are then learned to be represented by a low-dimensional vector. So this composed of two steps. First, we construct a component dependency network according to the historical component relations. The relation is extracted from the on-call engineer's records, where they have already some, or they already have some linkages. And then, based on the records, we'll build a graph with G equals to VE, and where V are are all the sets of components, and the E representing the set of existing historical incident links between every two components. If the two components have ever been linked together before, we would allow to link them composed to the graph. So then we use the node-to-vec algorithm to learn the low-dimensional representation for each component in the graph. And the incident description will also be important. It describes the symptom of the instance, including the location, the occurring environment, and the impacted services, etc. So this kind of information can greatly help linked incidents. To better deal with the uniqueness of incident description, we use a three-stage text representation learning method. In the first stage, the textual description in natural language is embedded word by word as a word vector using the fast tag method. In the second stage, we use the convolutional neural network layer to stack with the pooling layer to obtain the textual level representation. And in the third stage, with a fully connected layer to module the sentence semantic. And finally, we will combine both text and component structure by using a threshold to control whether two instances are related. In our experiment, we test our method, LiDAR, in the large online service system. We used 465 services and about 1,100 components in total, and the data ranges from January the 2017 to October the 2018. Here we compare with several state-of-the-art bug deduplicate methods, such as DWEN and deep learning-based bug deduplication method, and DBTM. And another is simple. It is a naive approach using historical linkages, and then is our LiDAR approach. So firstly, we tested the linked incident relations. The 10 subject applications are labeled as P1 to P10 in the table. It is evident that our proposed LiDAR can outperform other state-of-the-art bug deduplicate method in the incident linkage task among all these components. And we can find that the DWEN may sometimes obtain higher precision, while DBTM obtains extremely low recourse comparing to others, while LiDAR can obtain both high precision and high recourse scores, while LiDAR-T and LiDAR-C can obtain significant performance improvements comparing to others already. LiDAR can merge them together and obtain better performance. To prove the effectiveness of component dependencies, we have also investigated the effectiveness of component representation learning. We visualized multiple embedded component vectors with dimension equals to 64 from the following 7 services, which is data analysis, database and database query, and extension, network, and storage and supporting. So we can find out that our embedding method can cluster the components from the same service together in the latent space. This observation reflects the effectiveness of the component representation learning, which we can observe that the similar components like the data analytics service and the database service will be embedded at a similar position in the embedding space. And while some other services which is not related to them, like the extension service, will be embedded far away from their position. Further, we also evaluate the effectiveness of LiDAR in practice. We show a real case about virtual machine rebooting. One day, a population of customers has experienced the virtual machine reboot issue in some area, and according to the diagnosis records in ICM system, this instance is caused by the network failure. So to investigate which instances are related to the incident, we collect hundreds of incidents happened around time where the incidents are reported. So in this table above, we first list the top 16 most probable candidates ordered by the candidate linkage score using LiDAR. So after checking with the on-call engineers linking results, we find that 12 of 16 of them are indeed related to the investigated incidents. As presented in the table, top incidents happened at the cloud service system and storage components. So these components are recognized to be commonly affected by network issues. For example, the cloud service cache depends heavily on the network errors, while the performance of storage is largely influenced by the network as well. So as previously shown, the root cause of the investigated incident is a network failure. Thus, it is quite reasonable to find that the instance from the cloud service cache component and the storage components are likely to be linked with the investigated incidents. So here we have learned 3 lessons. Firstly, we should modeling the semantic information for instance to be effective. We use the Xian and CMS to learn the semantic representation in an unsupervised manner, and text information can be a great help for identifying these duplicate incidents. Meanwhile, it is important to consider the effectiveness of the historical component relations, which can help solve the location instance linkages and using the historical knowledge. And finally, using different types of data to mix them together is also important. Like here we use both component information and textual information, and, and also in this case, the validation set should be carefully chosen and carefully controlled. In our future work, we plan to continue our work in the following directions. Firstly, we will improve the link identification performance by incorporating more data sources, such as the time and location of the incidents and the severity of the incidents. And secondly, developing an online learning scheme is also important based on this current work, so that the new learned signals in the linked incidents can also be integrated into the model in real time. And third, extending the current work to combine with the other adjacent processes, such as the triage phase or the root cause analysis process, is also important for us. So these are all our works. Thank you very much.